Hi, just a heads up, I had to experiment with how to make this work, and what I'm doing is I'm watching the video that I recorded of the writing and then narrating it, so it's going to be possibly a little bit weird timing for this video, but I didn't have my desktop computer technology. So the problem-solving request for today was the last problem in the last homework, which I'm writing out the differential equation for that right now. And we're solving it with series, so we write out the series definition of our solution y as Cn x to the n, and then we take the derivatives. We're only going to need the second derivative, but if you take them manually, you kind of go in order. It would be okay if you just jumped right to the second derivative here. And we're just taking those derivatives using the power rule. Hopefully it's kind of familiar after we've been in this section a few days. And then our approach is always to go back to the ODE and plug in what we think the solution is. So we're plugging in those series definitions of y to the ODE we were given. And then eventually we want to try to solve for the things that we don't know, which are those coefficients c. So we're going to have to distribute that x squared plus 1 across the series for the second derivative. So we write out the x squared term, and then we go ahead and add on the 1 term. We're just factoring that series sort of into the x squared plus 1. And then that last term is going to be unchanged. And then from here, we're going to move that x squared into the series. And so all that's going to do is keep all our coefficients the same, but then we add 2 onto the power of x, because that's how multiplication of exponents works. And then multiplying the 1 in doesn't actually change anything for our middle term, and we haven't changed that third term at all. Now, when we simplify this first term, the x n minus 2 plus 2 is just going to become x to the n. And so we're going to want to turn every series into the power x to the n, because the first and last ones are that way. So if we want this middle series to be x to the n, I needed more space to fill it in, then we're just going to change everything that multiplies it. If we see an n, we move it up to n plus 2, because we're moving n minus 2 up to n plus 2. And then originally we started from 2, and that's what the first term was going to be. And so we're going to have to change the index to start at n equals 0. And we can see if we plug in 0, we get the same first term as we had before. So we haven't changed anything about the series. And then, as before, that last term, that last series is not changing at all. So now that the x's are the same, we want the initial index to be the same. So we just change the first to have initial index 0, and then we take away the two new terms we've introduced at n equals 0 and n equals 1. But those are both 0, so it actually doesn't change anything. And I just want to pause here and mention real quick that if you wanted to, you could switch everything to starting from n equal 2. But if you move the n equal 2 series down to n equals 0, you only have to change one thing compared to changing the other two series. But there's more than one right way to do this problem. And then the second two series, since they already started from n equals 0, they're unchanged at this point. And so we're going to combine all these into a single series that starts from n equals 0 and goes to powers x to n. So here I am just combining everything we had on the prior slide. Forgetting to write my coefficients for a second. And if we want this to be 0 for any value x, And for all powers of x, we're going to need the thing in brackets to become 0. And I'm going to pause real quick and mention that since we don't have any like leftover terms from switching the indices, we only have this one condition to work with. If that ever happens to you, it doesn't mean that something went wrong. It just means that you're going to be able to figure out all your coefficients following this one rule, as long as you set your first two initial like C0, C1. And the form WebWork wants this is an is equal to something an minus 2. So at the end of sort of pushing my symbols around, I'm going to switch it to match that notation, which I think is the easier way to match their format. So I want the bigger one on the left, so I'm going to solve for Cn plus 2 in terms of Cn. This is just an algebra problem. And then since I want that form that WebWork has, I'm just going to take away 2 from all my n's. So my Cn plus 2 becomes an, and then like my n becomes n minus 2, my n minus 1 becomes n minus 3, and then in the denominator, that n plus 2 is going to become n when I take away 2, and that n plus 1 is going to become n minus 1. And then my Cn becomes a n minus 2. And so now this is the form for the recurrence relation in WebWork. I'm actually going to simplify it a little bit so that I have less stuff to plug in when I actually start evaluating numbers. So I'm just multiplying out my terms. I see that 6 and minus 6 cancel out, so then I can refactor it. And then since I have an n in the numerator and denominator, I can also cancel those out. And then I want to move the minus inside so that I never forget to do it. So I just swap the subtraction in the numerator. And that's the relation I'm going to use for the rest of the problem. And I'm writing it down here so that I don't have to keep flipping back to slides when I fill that in.